Okay, a couple things. If you just came in and you didn't get a periodic table, we're giving you, I only have copies for one per person, so if you run out, you're going to have to, I don't know, find your own. These are great periodic tables, though. They've got a ton of information on the front and back. We'll refer to them multiple times during the semester. You can bring it on your exams, so hang on to it. I really don't have a ton of extras, so try and not lose yours. I next wanted to talk about some solution videos for extra example problems that I put up. I made these for Wiley. The people who make our textbook, they asked me to make some solution videos for people who choose to not use the textbook but rather use the online version. So these are available. They're in unlisted YouTube video links, right? And they go sort of by topic. And there's more or less 2 or so per chapter that we cover. So for this chapter, for example, you could see this one on interatomic forces, where I worked through an example on interatomic forces, or one on percent ionic character. So this is available. I posted it on in the announcements. You can take a look at this. Maybe I'll have the TAs add another column which says what chapter they correspond to and reorganize them that way, so you can follow along. I hope to make more in the future, but for now, at least we have this. If you want to see more worked examples in addition to the problems we do in lecture notes or that's in the textbook as it is, some students find that helpful. Okay, today, our learning objectives. If you remember last time we left off, we talked about enthalpy. We talked a fair bit about enthalpy, the heat that's involved in these reactions. And we ended class introducing the concept of entropy. And we even showed you with the rubber band how a reaction might be enthalpically not favorable, meaning it absorbs heat, but entropy actually dominates, and entropy turns out to be an important factor. So today, here's some of the things we're going to learn about. We'll learn how to predict entropy, at least increase versus decrease of entropy for different systems and reactions. We'll use then tabulated values of entropy and enthalpy to calculate the change of entropy or enthalpy for a reaction. We'll finally introduce Gibbs Free Energy as a way to bring both entropy and enthalpy components together. So instead of having to calculate both of them and wonder which one's going to dominate, we have a way to sort of consider them both at the same time. And then with that, we'll talk about the theoretical and experimental component of it. We'll talk about equilibrium. And if we have time, we'll even get into electrochemistry and have a neat demo. So let's start today where we left off, which was with the second law of thermodynamics, which has to do with entropy. So the first law of thermodynamics, let's just review really quickly. Let me pick on Andrew. Can you remind us, what was the gist of the first law of thermodynamics? Remember? Anybody remember? Want to give Andrew a hand? Wayne, is it?
Yeah, energy can't be created or destroyed, it just transfers.
Yeah, if energy can't be created or destroyed, we must just convert it from one form to another. So we said that the change in energy, du, was equal to dq, the heat going in and out of the system, plus pdv, the work that the system's doing on its surroundings. So the second law of thermodynamics is the following. It says the change in entropy, ds, must be equal to the integral of the heat going in and out of the system divided by the temperature. Right? And this must be greater than or equal to 0. That's the real key part here. The first part's less important. The second part's very important. That the change in entropy must be, at the very lowest, it's going to just stay equal. Meaning you take one system, you do something to it, at least the very least thing that can happen is that entropy won't change. And in the vast majority of the cases, entropy will actually increase. Entropy will never go the other way is what that's really saying. The universe will never shrink and become more organized. It will only expand and increase in entropy. That's really what this is saying. Right? So, how does entropy influence a chemical reaction? If we said that entropy increases is the only real outcome, then increasing entropy is going to be a favorable product, right? If you increase entropy, and again, that's just a degree of disorder. Sometimes it's easier to think of it in terms of the degree of disorder. If you increase entropy, then products are favored. If your reaction, as it's written, would shrink the entropy, then your products will not be favored. Your reactants will be favored, meaning you have to reverse your reaction, right? You're going to write it the other way. Okay? And we'll do some examples. Let's start with some clicker examples of this. So go ahead, grab your clickers. Found a way to make this work better, I think. Maybe. No, I didn't. Oh wait, I do. Okay. If that is our reaction, calcium carbonate as a solid, and again, today none of the points count on clickers. These are all just for practice. Make sure your stuff's working. Starting next class period, we will have both a reading quiz as well as clickers count for points. So today, the question is, if you have calcium carbonate, and this little S indicates that that's a solid, that's limestone, right? Calcium carbonate. That converts into CaO, lime, right? That's a solid as well, plus CO2 gas. Does the entropy increase or decrease in this system? So get your answers in. Okay, I'm going to wrap this up in just a second. Again, if you came in and you're using a physical clicker, you need to put it on channel 41. If you have a responseware, that's the session ID right below it. And these aren't for points today, but they will be on Wednesday. Okay, we're going to end this one. Does it increase or decrease? People think. What do people think? Most people think it increases. So somebody who thinks it's increasing, can you explain your logic, your sort of thought? Yeah, is it Anna? Anna.
So as it goes from a solid to a gas, the molecules become more free, making it more messy and disorderly, making the
yeah, if you ever, well, the rule of thumb is if you ever go from one product to one reactant to multiple products, it's usually going to be an increase in entropy because you have different species. Imagine you had one marble that is, when it was made, it was half white and half red. But then you split that marble into two. There's just lots of ways to increase disorder there. But then you split, the key word is that it went also from solids to a gas. Gases, we know, have lots more degrees of freedom. So definitely entropy is going to increase. Let's go to our next one. How about this one? You have silver solution, right? Silver ions in solution and chlorine ions in solution precipitating to form silver chloride, a solid salt. Increase or decrease in entropy? Okay, just a second on these. We won't wait very long on these ones. Answers in. A, increase. B, decrease. And I'm going to end it. Okay, do we think it increases or decreases? Okay, everyone thinks decrease. Somebody want to explain this? Can I pick on you, Zachary?
So, since you're forming a product out of it, your entropy is going to be decreasing since there's like less energy in the system as a whole.
Yeah. So gas molecules are really mobile, but ions in solution that are dissolved are pretty darn mobile, right?
Yeah.
So it's much more disordered before it comes together and forms this crystal. Rob, you want to add something?
Does an entropy never decrease?
That's a really good question, right? So we just said, he's asking a great question. I just said that in a reaction where entropy decreases, that reaction does not favor the product. So as written here, do you expect that this reaction from an entropy standpoint would happen? No. You would expect that this salt crystal would actually dissolve rather than form a crystal. That said, what might be happening? There's going to be a change in heat, right? So you've got these two things, and we haven't yet talked about Gibbs Free Energy, which we'll soon, which sort of brings entropy and enthalpy together. So even if something does become more ordered, there's the other component that makes up for it. Okay, let's go to our next one. One molecule of N2O4 splitting into two molecules of NO2. Both gas reactants and products are both gaseous. Kind of mentioned this one earlier. I'm going to spend a lot of time on it. Okay, I'm going to end this one. A, increase. B, decrease. People think that it would increase. Again, because you have two different molecules. Now that said, what about size of molecule? Should size of molecule play into our entropy question? What do we think? It should, and should it increase it or decrease it? Yeah, it does increase it. Imagine you've got a big molecule. You've got something like, let me jump over to one note. Let's imagine you've got like a big molecule like this. I keep on writing my polymers like that because it's carbon bonded to carbon. It makes this chain 109.5 degrees on these angles, right? But this is assuming that all polymers are exactly like that. And we know that that's not the case, right? With rubber band, we talked about this, that instead of being lines of like uncooked spaghetti, When you make polymers, they look more like cooked spaghetti where they're all over the place, right? So they can bend, they can twist, they can rotate back around, and that is far more disordered than this. So in general, bigger molecules have more entropy than smaller molecules, but if you're comparing one gas molecule versus two, then two wins out. Okay, let's go to our next one. This one is a closed can of soda versus an open can of soda. Entropy increase A or decrease B. Okay, I'm going to wrap this one up. Okay, who wants to give this one a shot? Entropy does increase. Anybody want to explain why? All right, Griffin, what do you think?
All the CO2 used for carbonating it goes out and it spreads out.
Exactly. Now, where is that CO2 beforehand?
It's mixed within, it's just pressurized under the can. It's contained.
So is it in the headspace or where? It's actually dissolved. Anybody taken like a can of, like a big bottle of Sprite that you can see through, and you like bonk it on the table and you see all these little like droplets of gas form all over the bottle and work their way to the top? It's actually dissolved into the liquid, which is weird to think about, that gas can be dissolved into a liquid, but it can, and in doing so, it's far less free than if it's in air, right? So when you release this into the atmosphere, you greatly increase the entropy of your system. Okay, and then this last one, we're going to rank these following compounds in terms of increasing entropy. CH2Cl, CH3Cl, or CHCl3. Which one has the most entropy? You'll notice that in all of these cases, the molecule is one carbon bonded to three other things. Oh, I messed up somewhere. That's supposed to be Cl2, I think. Yeah, I'm sorry about that. That first one's supposed to be CH2Cl2. Sorry about that. Make a note to fix that. So again, in each one of these molecules, you've got carbon in the middle, and it's bonded to four other things, hydrogens and chlorines. Okay, another 30 seconds. Get your answers in. Okay, got quiet. We're just going to end. All right, what do people think? Great. Most people got this right. It is B. Now, why is it 213 as opposed to anything else? What's your rationale? Somebody who got that right, can you explain what you were thinking? Remind me your name. Kyle. They're huge compared to hydrogen. Hydrogen has one proton, one electron. Chlorine is number like 30. I don't know. It's got a ton.
So it's so much bigger than
Yeah. And chlorine, think of it like this way. With all those electrons, they can all occupy slightly different spots. If you took a snapshot of it at a time, its electrons, even though they have an average spot as they whirl around the nucleus, they could be all over the place, right? So it's far more disordered. So bigger atoms also have entropy. So let's sum up some of the things we've learned from this series of examples. First off, molecule size. Bigger molecules have more entropy than smaller molecules. Second, in terms of phases, solid, liquid, and gas has far more entropy than liquid, which has far more than solid. Bonding, if you have a bond that allows rotation, like a single bond, carbon single bonded to another carbon, that bond can rotate, so it's more disordered than, say, like a double or triple bond, which are not able to rotate. Does that make sense? That's why if you ever see in OCHEM, when you see like acetylene, which is the stuff that they use in acetylene torches, it's this gas molecule. It's carbon triple bonded to another carbon. That is a really rigid bond. It can't rotate at all. So that's much less disordered than, say, methane, which is just carbon bonded to hydrogens. Okay. Next, you've got dissolution. We already talked about that. And then atomic mass. The higher the atomic mass, the more the electrons, the more protons, the more disorder that can have, right? So these are just general rules. I'm sure there's exceptions, but these are general rules that help us think about entropy. Yeah, Griffin?
This is kind of why larger, like usually polarity or molecules like uranium will not have like smaller half-lives because they're more unstable.
That's a really good question that I don't know the answer to. He asked a great question. He said, say really big things that are radioactive, like uranium. Is entropy involved in this decision? It's got all this entropy or all this disorder, but it could be even more if it splits into two smaller atomic number elements. I don't know the answer to that. I could maybe try and find out. It's a great question. Okay, next let's talk about Hess's law. Hess's law has to do with, all right, for these reactions, generally speaking, things go up or down. Now we're going to talk about how we can calculate them. And the key part of Hess's law is that you can calculate the entropy change or the enthalpy change if you do it step by step or all together. That's the real key takeaway. So for example, if you've got this example here, you start out with phosphorus chloride, I don't know what you call it, PCl3. You're going to add chlorine gas to it to form PCl5. So we can calculate the change in entropy and enthalpy if we know the parts. Here's what I mean, right? The top two are two reactions, right, which are not the ones we're looking for, but we could combine these top two reactions in a certain way to achieve the final reaction, right? And when I say combine, I mean we could take these and we could flip them, we could make them negative, we could do whatever we want, we could divide them or multiply by certain numbers, and then when we add them together, we'd get this reaction. So first question is, what do we have to do to add those two reactions together and get this final thing that we're looking for? What would you guys do? Which one would you flip? Yeah, the first one's definitely got to be flipped because its product is one of the reactants that we're looking for. We want PCl3. So you're going to flip it. Now, if you add those two together like that, are you okay? No, because you're creating 2 moles of the PCl5 and we only want to make 1 mole. So we need to flip the first equation and then we need to divide the first and second equation both by 2. When you add it together, you should get that. So what Hess's law says, and it's clever, it says if you do that, when you flip a reaction, make the product's reactants, you change the sign of the enthalpy for the reaction. This is the change in enthalpy for the reaction, delta HR, change in enthalpy for the reaction. When you flip it, you change the sign, so that's going to become positive. And when you multiply or divide the number of coefficients here, you can do the same thing with your change in enthalpy for the reaction. So we're going to divide both these numbers by 2, and we're going to flip that one, add them together, and what do you get? Which is the right answer, A, B, C, or D? Yeah, Griffin?
As well, whenever you increase the reactants for both, so they have similar CO2s.
Yeah, you also want CO2. You want it to be the exact same, such that when you add it together, you have the same. Okay, so take a shot at this. You can work with a neighbor if you don't know what to do. Emily is our TA. If you've got a question, you can raise a hand. Emily and I can walk around and help you. Okay, I'm going to go ahead and end it in just a moment. Again, these aren't worth points today. You don't need to be worried about making sure you have the right answer today. Okay, I'm going to end it. And people think the answer is... And I think that's the right one. In future, I'll make it have a little check mark beneath the right one. I think it is number C, though. Is that C? I think it's C. Okay. Okay, so that's Hess's law, meaning if I give you a bunch of reactions which they don't look like the reaction I'm looking for, but you can combine them together in one way or another, you can combine the change in enthalpy or the change in entropy in the same way. So that was with change in enthalpy. We could have done the same thing with change in entropy. Let's go to this next one. there exist tabulated values for what are called the standard enthalpy of formation, or the standard molar entropy for compounds. And the question in the back? Let's write it out. So the question was as follows. So it's right here. These were the equations we had. We decided that in order to add those first two equations together to create the third, we had to flip the first one, and then we had to divide both the first and second equations by 2. So what we're going to do is we're going to flip the first number, negative 640. So negative 640, that's going to become positive 640 because we flip reactants to products, and then we're going to divide that by 2. Right? Meanwhile, the other equation, we're not going to flip it because it has the right product that we're looking for, but we do need to divide it by 2. So it's going to be negative 887. Negative 887, we're going to divide that by 2. And when you add this and that together, you get the negative 124 kilojoules per mole of reactant produced. Okay? Does that make sense? No? We're going to do another example in just a moment. Okay, there's another example coming up right here. First off, you've got tabulated values of what's called the standard enthalpy of formation, or the standard molar entropy. What these are is chemists have put together tables that says under certain conditions, say 1 atmosphere of pressure and at room temperature, this is the change in enthalpy or change in entropy to form that compound from its constituent components. That's the key part, meaning if you start with elements in their elemental form and you put them together to make this compound, what's the change in entropy? Right? For example, if you're trying to make CO2, you have to start with carbon and oxygen, right? In their elemental forms, you're going to combine those, and it tells you basically what's the change in enthalpy or entropy to form that compound. And so there's big, long tables of this. You can pull them up. There's lots of free ones that cover a lot of species. And the key thing is that if you're talking about something, it's the formation from its elemental state, which means things like aluminum, again, this is at room temperature, 298 Kelvin, that's about room temperature. Solid aluminum metal, to form solid aluminum metal, you're just starting from solid aluminum metal. So the change in the enthalpy, the change in heat involved is nothing. Because you started aluminum metal and you're just making aluminum metal. So there's no absorbing or releasing heat. But there is a change in entropy because because it went from room absolute zero up to room temperature, it's going to be vibrating a little bit. It's going to have some entropy, right? And because it's a solid, this entropy number is not very big, 28.3. If you look at a gas, see these aqueous signs, they're going to be larger. And if you find a gas somewhere on here, it's going to be far larger, right? These gases are really big. So what's great about these tables is that you can look up for individual elements what their standard formation enthalpy or entropies are, and then you can write a reaction and use these standard values to write out what the change of entropy or enthalpy would be for the whole reaction. Let's do an example. Right? So right here, N2 combining with 3 H2 molecules to form 2 ammonia molecules, NH3. To do this, all we have to do is find out what our table values for these things are. Let's do enthalpy first. To find out the enthalpy, first we need to figure out the standard enthalpies of formation for these 3 species. So ammonia, let's look up ammonium first. So, search for NH3. That's aqueous, but in this question I think I wrote gas. Yeah, we actually want a gas. And aqueous ammonia, dissolved ammonia gas in a liquid, is going to have very different entropy and enthalpy than the gas. So let's move this and search for our next one. There we go. NH3 is a gas. Here's its enthalpy, its change in enthalpy of formation. So the enthalpy involved when you go from N's and H's, right, put them together, it's negative 46.11 kilojoules per mole. Negative 46.11 kilojoules per mole of substance created. Now, what do you think H2 and N2 are going to be? They're going to be 0 because remember, it's the change in enthalpy when you go from its elemental state to whatever you're talking about. And in this case, they're in their elemental state. These are both going to be 0 kilojoules per mole. Now, the only catch now to figure out the change, what we're going to call the change in enthalpy for the reaction. So delta means change, little r means for the reaction, H is enthalpy. So the total change in enthalpy for this reaction is going to be products minus reactants. We're going to sum up the products. That weird looking E thing is the sum of products minus the sum of the reactants. So reactants are easy. They're just 0. 0 plus 0. And then products, we need to take 2 times negative 46.11 kilojoules per mole. Now, why do we need the 2? Is because we're actually creating, in this, as the reaction's written, we're creating 2 moles of ammonia gas, right? So in this case, it's going to be pretty straightforward. I think that's our next clicker question. Okay, so the next clicker question, I've done the first part for you. The change in enthalpy, you know it's going to be 2 times negative 46, which is about negative 92. The next part is more challenging. You have to figure out the change in entropy. So you know the answer is going to be either B or D. So then what I want you to do is figure out what's the change in entropy in the exact same way. It's going to be products minus reactants. Make sure you multiply by 2 or 3 or whatever the number is, but do products minus reactants and figure out whether the answer is B or D here. So this table tells you what the standard entropy values are. And if you got a question, we've got 2 TAs here now, so just feel free to raise a hand. We're happy to walk around and help. Remember, it's the sum of the products minus the sum of the reactants. Okay, can spend one more minute and we're going to move on. We're going to write it out together and work on it anyways. Good? Any questions? Okay, we're going to wrap it up. B or D? Is it B or is it D? Get your answers in. People think it is... Okay, B. Or, sorry, D, excuse me. It is D. So let's write out how we can solve for this. Again, we're solving for the change... For the reaction, the change in entropy, right? Delta RS is going to equal, again, it's products minus reactants. So it's going to be 3 times the entropy for our ammonia, which is 192.45. That's got weird units of joules per mole Kelvin. That's going to be minus the sum of 3 times hydrogen, which is 191.61. Plus 130.68. Again, this has the units of joules per mole Kelvin. And that comes out to negative 320 joules per mole Kelvin. Any questions on this? Yeah, Tom.
How did they come up with those values?
How did they come up with those values? It's a great question. I'm not going to get into it because it's a big tangent. It has to do with measuring heat very carefully in and out of the systems. Right, that's called differential scanning calorimetry. If you want to learn more about it, we teach a course 3011 where you learn how to use instruments like that, but I won't say more about it in this class.
So you just burn it?
You burn it. You basically burn it. You measure heat going in and out as the sample's temperature changes. That's really what's into it. Is it Logan?
Yep.
Yeah.
You said products 3 times 192?
Yeah, and the reason I did that is because if you look at this chemical equation, 1 mole of N2 gas combines with 3 moles of the H2 gas to form 2 moles of NH3. So that's what the 2 and the 3 and the 1 are. It's from the coefficients in your balanced chemical equation.
Yeah, but we only have 2 moles of NH3. You wrote down.
Did I mess up something? Oh, yeah, I did.
Okay.
Yeah, thank you. Thank you for catching that. Will not be the last time. Other questions on this I can answer? Okay, I'm going to move on. That cleared your question from before, kind of?
was like when we had the three equations. Once we had it out, so I just figured it out.
Okay. If you want to see more examples of Hess's law, we have from previous years, old tests and stuff. I can make sure that the TAs have those. We can work through examples on those. Yeah, question?
Do you post your clicker questions anymore?
You know, I haven't in the past, but these videos are online, and Emily is she's doing great of noting when we talk about different things. So there's a timestamp hyperlink in the YouTube video, so you can always go back and rewatch and see them there. I think that's probably the easiest way for us to post them. Okay, so now finally we get to the question of, all right, we know that enthalpy and entropy both exist, and how do we figure out which one dominates? We need a new energy term that takes into account both these things, and that thing thankfully exists. It's called Gibbs Free Energy. Gibbs is named after one of the very first American PhDs to ever get a PhD in what is now America, right? Brilliant guy. And what he basically realizes is that, okay, the Gibbs Free Energy takes into account enthalpy in this way. It's equal to H minus Ts. So if you know what the enthalpy is, you minus the entropy times the temperature that you're at, that would give you the Gibbs Free Energy. So let's write out a generic reaction. Here's our generic reaction. You've got N sub A, that's the number of moles of compound A, right? Na compound A, Nb compound B, right? So you're combining some number of moles of compounds A and B, and you're going to form some number of moles of compounds Y and Z. We can write out what the Gibbs free energy for that expression would be, right? The Gibbs free energy we know is equal to, well, first off, enthalpy is equal to H equals U plus PV, right? And we know that G equals H minus TS, so we could plug in U plus PV in there, right? And then if you look, what we really care about is the change in free energy. We care less about the absolute value of free energy. What we really care about is as you go from reactants to products, does it step up or down in energy? That's what we really want to know, right? This is the energy that we're going to talk about for the rest of the semester. What does the energy of the system do? Does it go up or down? We're talking about Gibbs free energy. So it's dG that we really want to know about, because G is going to depend on lots and lots of variables: temperature, pressure, the number of moles of all these different species. And so dG is what we really want to care about. So the first thing is, let's figure out what is dG dt. If you take the partial derivative with Gibbs free energy with respect to temperature, and you hold everything else constant, P and N for all species, so meaning the number of compounds of A, B, Y, and Z are all staying the same. Number of moles isn't changing. Pressure's not changing. The only thing that's changing is temperature. What should that be equal to? And then likewise, if you take dG but dP, so you're going to keep everything constant, temperature, the number of moles of all your different species, but you're going to change pressure. What should these two expressions equal? What's dG dt? Well, if it helps, you can plug it in up here. H is U plus PV, now minus TS. So if you take dG dt of that expression, what are you left with? Negative S, right? The negative of the entropy. That's right. And then what about, and then we'll write dt, right? Because you took the derivative there. So it's minus S dt. Now what about P? Yeah, it's going to be positive V, and then we write dP, because we took the derivative of pressure, right? This will be important next chapter. We're going to come back to that. Okay, the partial derivative of free energy with respect to temperature or pressure, we can predict what it should be if we know the entropy and the volume of the species. That'll be important later. Okay, I'm going to skip some of this. For the sake of time, I'm going to skip that. Let's talk about now this. The free energy equation depends on both the theoretical component as well as an experimental component. What on earth are we talking about? So the theoretical component as well as an experimental component. Here's what, let me write these actually in color so it's easy to see. The theoretical component is this part. The experimental component is this part. And I think the easiest way to think about this is that the total change in free energy system, it's one thing as it's written on paper. Imagine you have gasoline combining with oxygen to form CO2 and H2O. Is free energy favorable for that reaction? You betcha. It gives off heat and it becomes more, and entropy increases. So it definitely wants to happen as it's written on paper. Right? So theoretically, you'd say gasoline combining with oxygen to form those products is favorable. But then you've got the experimental component, right? What if this is taking place in a chamber where there's no oxygen initially present? There's only CO2 present. Now can that reaction as it's written take place? Definitely not. So there's an experimental limitation on it. So when you think of the change in free energy for a reaction, it depends not only how it's written on paper, right, the balanced chemical equation, it depends on the species that are present in the beaker where this is actually happening at. Does that make sense? We'll show you some examples of the implication of that in a moment. Right? Because of that, we have to introduce this RT natural log of Q, where Q is our reaction quotient. Those that have taken Gen Chem 2 have seen this before. If you haven't, we're covering it right now. The reaction quotient can be written for a chemical reaction as follows. If you have Na of compound A combining with Nb number of moles of compound B to form Ny number of moles of compound Y plus Nz number of moles of compound Z, we can write the reaction quotient as follows. The reaction quotient Q, if these are all gases, actually I've got space down below. Q, if they're all gases, then Q equals products over reactants. You're going to take the partial pressure of Y raised to the number of moles of Y multiplied by the partial pressure of component Z raised to the number of moles of Z, divided now by the reactants, the partial pressure of component B raised to the number of moles of B, multiplied by the partial pressure of component A raised to the number of moles of A. So that's kind of a mouthful, right? It's really just products over reactants. Now, what are we talking about when we say partial pressure? I'll give you just a minute to finish writing that down. When someone's ready, or in the back, is it, I don't remember your name. Spencer. What are we talking about when we say partial pressure?
Is that just the percentage of it?
Yeah, right? If you have, if your total pressure, P total, equals 1 atmosphere, but you know that, say, 70% of that comes from component A, then your partial pressure of component A would be 0.7, 100 times 0.7, right? So it would be 0.7, or times 70%, excuse me, so it would be 0.7, sorry, 1 ATM times 0.7 would give you the 0.7 ATMs, right? So it's the partial pressure. We've got that written down here below somewhere. Right here we talk about partial pressure. So for a moment, let's come back to this, right? In the case where this equation is all gases, it's pretty easy to do. Question?
Is the Na, Nb, and Y, are those concentrations, or are they just...
No, that's the coefficient in the balanced chemical equation. These are just the coefficients, 1, 2, 7, whatever that number is, right? So the partial pressure gets raised as an exponent to however many of those were. So if we go back to our equation here, let's write it for this one really quick. What would be the reaction quotient for this one? These are all gases, right? So Q would be the partial pressure of ammonia, whatever that value is, that's going to be squared, divided by the partial pressure of H2 gas, that's going to be cubed, multiplied by the partial pressure of N2 to the 1. Okay, any questions on this? Question or itchy head? Itchy head, looks like. Now, what if A and Y, right? You've got components A, B, and Y, and Z. What if components A and Y were either liquids or solids? How do you have a partial pressure of those things, right? Well, in the real world, when you guys take thermo, you'll find out that, in fact, a solid can have a significant partial pressure, right? If you've ever taken say like ammonia, when you open up like your pine sol, you smell the ammonia. Even though it's a liquid, it has quite a high partial pressure. You can smell it. Or like CO2, dry ice is just CO2, right? And that sublimates and it has a pretty high partial pressure. But for this class, we're going to make it way simple. We're going to make a huge approximation that all solids and liquids have what's called an activity of 1. And that changes this significantly. Now Q would be written as follows. Q would be the activity of Y raised to the number of moles of Y times the partial pressure of Z raised to the number of moles of Z divided by the activity of A. Oh gosh, I'm sorry, we're using the same letter A. That's unfortunate. Raised to the number of moles of A, multiplied by the partial pressure of B, raised to the number of moles of B. And the activities, these are just equal 1. So basically you can just ignore them. You can leave them off. They're not 0, they're 1. We say they have an activity of 1. Or in other words, when you write these reaction quotients, ignore the solids and the liquids. You only need to write it for the gaseous species. That is not strictly true. That is a huge approximation that we will use in this class that you can't get away with in all real-world cases. Any questions on this? Yeah?
So the reason that only Y and A get changed to B and C instead of pressure?
Is because we stated that they were solids and liquids. If I'd said B and Z, then it would be reverse, or whatever else. Or if they were all solids, then it would all be 1. Q would be just 1. It'd be 1 divided by 1 if they were all solids, right? Then we won't have to worry about that term. Yeah, question?
Can you say what Q means again?
Let's come back to Q. Great question. So first off, where does Q come from? We're talking about dG, the change in free energy for a reaction, right? So you've got it right here. First off, if you remember, we have PV equals nRT. Anybody remember this from Gen Chem? What is this talking about? It's called the ideal gas law. And it says, let's say that you take a gas and you double the pressure, but you keep the volume constant. If this gets doubled and this stays the same, what must happen over here? Yeah, for this to stay constant, you have to change the temperature or the number of moles in your system, right? If moles aren't changing, then temperature has to change, right? So PV equals nRT is where we start from. Now, if you remember, we also had that dG equaled, we just wrote this up above, VdP minus SdT, right? That's the partial derivative of the free energy with temperature and pressure. And we're going to say that the number of moles isn't changing, so you don't have to worry about that just yet. So you've got that. Therefore, we want to figure out dG for the system, but we can do that by substituting in for volume. If you solve for volume here, volume equals nRT over P, right? So if you plug that in, and then you assume that it's happening isothermally, meaning no temperature change, that allows this term to go away. That term goes to 0. So let's plug that in. Now we've got dG equals nRT over P. We're going to integrate both sides of this with respect to dP. So anything in this equation, meaning all this stuff up here that's not P, can come out of the integral. So now it looks like 1 over x dx. And what's the integral of 1 over x dx? Natural log of x. So that's where this term comes from. This kind of funny equation comes from that sort of approach. And it's surprising that that actually works, right? But it does, right? So the change in free energy, the change in Gibbs free energy for a reaction, delta RG, is going to be equal to delta RG naught, meaning the change in Gibbs free energy under standard conditions, right? Using those tabled values, these things, right? They've got your delta G's of formations, right? If you were to look up all those for the different reactants and products, and you did the products minus reactants, that would give you this term, which we're going to call the theoretical component, right? But then you have to add this plus RT natural log of Q. And Q is just a way of measuring basically the degree of what's your ratio of products to reactants is kind of what it's measuring, right? If you remember from last 2 classes ago, we talked about Le Chatelier's principle. What was Le Chatelier's principle again? Somebody remind us? Le Chatelier's principle, which was, Hayden.
When you have a chemical equation, it will shift the products and reactants depending on stresses on the equation.
Yeah, basically there's an equilibrium. So imagine, and in future years I'll be clever and I'll remember to do this. Imagine that I brought like a case of Snicker bars, and I'm like, Thomas, you like Snicker bars? He's like, of course I like Snicker bars. I'm not a barbarian, right? So I'd say, well, eat a Snickers bar. And the reaction as written, like uneaten Snickers versus Snickers in Thomas's stomach, is favorable to start with, right? But if I keep on feeding him Snickers bars, there's going to reach a point when those Snicker bars come back out, right? We can imagine that happening without actually having to do it. That's kind of what this Q is getting at, that you can drive a reaction so far forward that it can actually go back again. So it has to do with the equilibrium of your reaction. Thomas?
Yeah, what's partial pressures have to do with the materials? Are we building chambers here?
You will see. We'll have great examples. On the next homework, you actually talk about what's happening in the engine of a car, and you'll see your very first example of this. When you combust something in the engine of a car, and you're talking about the products that get created, and there's products that you want and don't want, you're going to see your first example of that. So hold that thought to homework 2. Okay, real quick, what is air composed of? Before we can do an example of this, let's talk about what is air composed of. What is air? What on earth is air made of? Which of these 4 things is air? Okay, what do we think? I'm going to wrap it up. A, B, C, or D? What is air made of? And obviously it changes a little bit here and there, but it's pretty much constant. Okay, I'm going to end it. People think what? You're right. It is mostly nitrogen, right? Surprising, like we're breathing 78% nitrogen. Only 21% of what we breathe is oxygen, right? 78% N2, right? Which is why if you work in the lab with nitrogen, it's not super dangerous unless it displaces all of the oxygen, at which point it could become dangerous, right? Then you've got 21% oxygen. This is why when grandma needs to, her lungs aren't working well, they give them pure oxygen because you're getting rid of that 78% of nitrogen, which your body's not using, and just getting the pure oxygen, which can help people that aren't breathing well, right? Right, and then 1% of everything else, basically. Right? We've got 4 minutes left. Let's, we won't get to the penny battery. We'll do that next time. Or do we want to do it today? Let's do it next time. Is that heartbreaking? You okay? Okay. Okay, so delta RG, excuse me. The R goes right here. All right, sorry about that. The change in the free energy for a reaction, what that does is it tells us the direction of a reaction at any temperature, right? No matter what's in the beaker, right? I can calculate if the reaction is going forward or backwards. If I know what's in the beaker and I know the temperature, I can calculate it, right? And we know that the change in free energy has both enthalpy and entropy components. So imagine this for a minute. We'll do this as the last thing today. If the change in enthalpy, that's not what I want. I think I want the next one. Sorry. Next one. Oh, that's it for today. All right, we'll just do this one by hand. We'll start next time. But if the change in enthalpy is less than 0, meaning it's favorable or unfavorable. Change in enthalpy is less than 0. Is that favorable or unfavorable? If it's less than 0, that means it's a negative number, so you're actually exothermic. So that's favorable, right? So if delta H is less than 0, that's a good thing. And then delta S is greater than 0, so the entropy increases. Is our reaction favorable? Definitely favorable. And you could figure it out yourselves, right? Delta G equals a negative number minus, right? Minus a T is always going to be positive. It goes from 0 and up if it's absolute numbers, right? From absolute 0 to up. So in Kelvin. So that's a positive number multiplied by a positive number, right? So will that ever be positive? That will only ever be negative, right? A negative number minus more numbers is going to be negative. So that is definitely delta G will be negative. A negative number, right? Now think of it the other way. What if delta H is positive, meaning it's endothermic, but delta S is negative? What will this one be? I heard somebody say positive. It will always be positive, right? Because again, in this case, you've got a positive number minus positive temperature minus a negative number. That will always be positive, right? So that reaction will never happen, right? But what about these two scenarios? What if delta H is greater than 0, so it's endothermic, but entropy increases? We know that endothermic says it shouldn't happen, but entropy says it should. Which one, how do you know what's going to happen? It depends on the temperature, right? Because you've got a positive number minus a positive temperature multiplied by, we said this is great, right? So depending on the temperature here, it will dictate whether that happens or not. And we're just about out of time, so we'll pick up here next time.